The second topic for today's lecture is going to be about the surface integrals. So let's assume that we have this surface S in three-dimensional space, this one right here. This one is surface S and we want to perform integration on it. So why don't we start with the equation for this surface S, and it's going to be this equation right here. Function of x, y, and z equal to constant value c. And this is going to be the main equation we use to represent any surface S in 3D. So let's make a note right here. This one is for surface S in 3D. And it's the same as this one right here. Function of x, y, z equal to constant value c. Now that we have the equation, we can perform the integration on it. And today we have two versions of the integrals that we are going to learn. So let's start with the first one. This first one right here, we are going to perform integration in order to find the area of this surface S. So first one is for finding area of surface S. And as you can see here, surface S that you have right here is curvy. Definitely curvy. So the area of this is not going to be a simple geometry. Alright, and we need to rely on the integration to find that. And that is the first type of the integral of today. And now moving on to the second type of the integral. In this one, we are going to perform integration to find the integral of any function on this surface. This one is going to be a little bit different. So this one is for finding integral of any function, and let's call it g of x, y, z. Notice that this one is different from this f right here that we have. Alright, any function g on the surface S. On S. Alright, now let's start with the first one, which is supposed to be the easier one. So let's start with this. Finding the area of this surface S. And we are going to use calculus. And as you know, when it comes to calculus, we like to cut things into pieces. And then we find the property of each piece, and then we add them all together in the end. Alright, so here we are going to cut this surface S into pieces. Find the area of the small piece, and then in the end, we add them all together to find the total area. So let's do that. Let's cut this surface S into one piece right here, right in the middle. Okay, I'm going to do this. Okay, something like that. Now, let's assume that this piece is very small. I make it big to make it clear to you. So this one is really, really small. Alright? Okay, now, I realize that the surface S is curvy, which means that the edges of this piece that I cut is going to be curvy too. But let's assume that this piece is so small that all the edges are considered to be straight, which means that this piece is going to become a parallelogram. So let's make a note right here that this one is tiny parallelogram. Okay, and we want to find the area of this piece. So I'm going to call this piece, area of this piece, dp. Area of this equal to dp. Alright, big P. Okay, now the next thing I am going to do is to find the projection of this piece onto the plane under it. Okay, so let's assume that the axis that we have is in this format. Z-axis, x-axis, and y-axis. So what we have right here is xy plane down here. XY plane. Okay, let's find the projection of this dp onto the xy plane. So it should be something like this. Going down, straight down, and let's stop here. Same with this corner. Alright, all four corners. So here we are going to get the projected piece on the xy plane, it should look something like this. Okay, let's highlight this. Okay, this one is dp. Oh, this one up here is dp on surface S, and this one down here is dA. The area of this piece down here is going to be equal to dA. Alright, so now we have two pieces. The next thing we are going to do is to put reference vector on each one of them. So I am going to put a vector that is orthogonal to each piece. So let me put this one right here. Okay, black one, this one right here, orthogonal to dA and also to xy plane. Okay, orthogonal to dA, and I'm going to call this vector a hat. Okay, this one is a hat. Okay, let me change this. I'm sorry. Okay, this one is a hat. Okay. Alright, a hat orthogonal to dA. And not just that, I assume this a hat to be a unit vector. So why don't we put a box around this? A hat orthogonal to dA, and a hat is also a unit vector. Keep that in mind. Alright, that is the reference vector for dA. And we are going to do the same thing for the piece on the surface S, dP. So we want to find the vector that is orthogonal to dP, which means that it has to be a vector that is orthogonal to the surface. It has to be orthogonal to this equation right here, this surface right here. And that vector is going to be the gradient of f. So if you find the gradient of f, it's going to show up as something like this. Okay? And this vector is supposed to be orthogonal to the surface S and also to dP. So this one, okay, let me highlight, make this a little bit more straight. Okay, this one is gradient of f x, y, z. What about I put it right here? This one is gradient of f. Alright, now we have two pieces and each one of them has the reference vector. Now we are going to find the relationships between them in terms of angle. Okay, so why don't we start with the angle between the reference vectors? So I'm going to bring the a hat to the surface. So I'm going to bring this a hat up here. So it's going to show up as this vector. Alright. This one is going to be a hat which is orthogonal to dA and a unit vector. And as you can see, we are going to have this angle between them. Alright. Now we are going to call this angle between a hat and gradient of f as rho. We are going to call this angle right here rho, which is the angle between gradient of f and a hat. Alright, now that is the relationship between gradient of f and a hat. But I want you to notice something. If, as you can see here, both vectors are orthogonal to each piece. Alright, now if the angle between the vectors is rho, then the angle between the pieces themselves are going to be the same. So let's write that down. Angle between gradient of f, the reference vector, and a hat, and in this case we know that it's equal to rho. Alright, is going to be equal to the angle between the pieces themselves, equal to angle between the pieces dP and dA. dP and dA. So in terms of the angle between dP and dA, it's going to be equal to rho as well. So we are going to have this angle rho between dP and dA. Now let's keep that in mind and let's take a look at this diagram. So we have this, okay, y-axis and x-axis, and let's have this vector A. Alright, this is vector A, and we want to find the length of the projection of A on the x-axis. So we want to find the length of this vector A on x-axis. Okay, let's put x-axis right here. We want to find the length of this projection. And the length of this projection is going to be equal to, okay, let's change this to capital A. The length here is going to be equal to absolute value of A cosine theta, and theta is going to be the angle between them. Right? So what you get from here is that if you want to find the length of the projected piece, it's going to be equal to the length of the original piece times the cosine theta, and that theta has to be the angle between them. Okay, once again, length of the projected piece equal to the length of the original piece times the cosine of angle between them. And we are going to use this concept with dP and dA. Let's take a look here. The area of the projected piece, dA, is going to be equal to the area of the original piece, dP, times the cosine of the angle between them, times the cosine of the angle between them, and the angle between them is rho. So we have this relationship between them, dA and dP. dA equal to dP times cosine rho. So let's move things around. We have this dP equal to dA over cosine rho. Alright, now let's leave that for now. Let's take a look at the relationship between the vectors, the orthogonal vectors, gradient of f and the a hat. So let's write it right here. We are going to find the dot product between them. Dot product between gradient of f and a hat is going to be equal to the absolute value of the gradient of f times the absolute value of the a hat cosine angle between them, and that is rho. Okay, now we know that a hat is a unit vector. We have assumed a hat to be unit vector, so this one right here is going to be equal to 1. So let's move things around and I get this relationship. 1 over cosine rho equal to absolute value of gradient of f divided by dot product between gradient of f and a hat. And now we are going to assume the angle rho to be less than 90 degrees. Assume rho to be less than 90 degrees and also greater than 0. In this case, cosine rho is going to be positive. In this case, we can add this absolute value here because cosine rho is going to be positive, so the whole term has to be positive. So we are going to use this in the relationship that we built right here. 1 over cosine rho equal to the absolute value of gradient f divided by the absolute value of gradient f dot a hat. So let's put it right here. So in the end, we have this dP equal to 1 over cosine rho, which is gradient of f, absolute value, divided by absolute value of gradient of f dot a hat, alright, times dA. Alright, I think I need more space here. So let's put this equal to dP. So what we have right here is the area of one piece. This one right here, dP, is area of one piece. But we want the area of the whole surface S. So we need to perform the integration to add them all together. This is just one piece. We need to add all the pieces. So we perform the integration both sides. Integration of the dp, and we perform the integration with respect to differential area. And we know that differential area, in the end, it becomes dx dy or dy dx, so this has to be double integral. Alright, so we add them all together, and when it comes to the double integral with respect to differential area, we have to perform it over an integration domain. So we need this integration domain R. And in the end, this is going to be equal to the surface area of the surface S. Area of S. So there you go. We have derived the formula for the first integral of today. So let's put that in the box. So this one right here, first formula, area of S. Okay, area of S equal to double integral of absolute value of gradient of f divided by absolute value of the gradient of f dot a hat. And we perform the integration with respect to differential area, dA. And for this one, it could either be dx dy or dy dx. Which one to go for? That depends on the situation. And of course, we have this integration domain R. And the integration domain R is this projected of the surface S. Projection of the surface S on the xy plane. So we are talking about this projection right here. Okay, this one right here, the whole piece right here, that is the integration domain R. So make a note right here that this is the projection of surface S. And in most cases, it's going to be xy plane. So let's put a box around this formula, first one. All right. Now, moving on to the second formula. This one is for the integral of any function g on S. So in this case, all we need to do is to add this g inside the formula that we just derived. And we got this integral. Okay, so we just need to add this g inside the formula. And we have this integral. This second formula, integral. Okay, let me fix this. I'm sorry. Integral of g on S equal to double integral. And let's add g to here. G of x, y, z times same terms. Absolute value of the gradient of f divided by absolute value of the gradient of f dot a hat. Alright, and times dA right here. And let's put a box on this one. Second formula. And of course, this one has the integration domain R, and it's the same as the one we had before, which is the projection of S onto the xy plane. And keep in mind that we have A right here inside the formula, and this A has to be the vector that is orthogonal to R. So make a note right here that A hat is orthogonal to R. Okay, this one same. A orthogonal to R. So if you project this S onto xy plane, this A hat right here is going to be K hat. So this one is going to be K hat for xy plane projection. Alright, there you go. We have two formulas today. One for the area of the surface S. This first one, area for the surface S, and this one is for the integral of any function g on the surface S. Number two. So let's move on to some examples in the next slides. In this example, we are supposed to find the surface area of a paraboloid, and we are given with this equation right here. x squared plus y squared minus z equal to 0. And this surface is cut off from the top by the plane z equal to 4. And that is all the information that we have. So the first thing we are supposed to do is to plot this surface in the space. And it turns out that it has been plotted to you. So let's use that. Let's use this diagram on the left hand side. So this one right here is the paraboloid. And as you can see, it's cut off from the top at z equal to 4. So at this point, the paraboloid is cut off. So there you go. You have this ball in the space, and we are supposed to find the area of this surface. Alright, the surface of this ball. Now, as you can see, this is the area of a surface in the space, so we are going to use the formula that we just derived. So let's bring that formula here. So this is area of S in the space equal to double integral, alright, of the absolute value of the gradient of f. So same formula, absolute value of the gradient of f divided by the absolute value of the gradient of f dot with a hat. Okay, absolute value of gradient of f dot with a hat. And a hat has to be the vector, unit vector that is orthogonal to the integration domain. Okay, and perform the integration with respect to the differential area. And we have to do that over the integration domain R. Alright, so that is the main formula that we need. So let's put a box around this. Okay, main formula. Okay, now we need to find out about the components inside this formula so that we can continue with the calculation. Why don't we start with this f right here? We need to know about this f. Right, and this f is going to be the equation for the surface in the space. So let's take a look at the equation that we have. This one right here, the paraboloid equation. By now we know that the equation, the form of the equation that we need for this surface is going to be in this form. Function of x, y, z equal to c. By now we know that this is the format of the equation for the surface in the space. And when we look at this equation for the paraboloid, we know right away that the left hand side is function of x, y, z. So the left hand side of this equation is going to correspond to f of x, y, z. So let's write that down. F of x, y, z. Okay, what about I put this right here? This one is f of x, y, z, the left hand side of the equation, and the right hand side, 0 right here, is c. So we have f equal to c right here. Now, this is the first piece of the information that we have, so let's write that down. Function of x, y, z that we need is going to be equal to x squared plus y squared minus z, the left hand side of the paraboloid equation. Now let's take a look at the next component that we need to know. The vector A, unit vector A. And since we know that this unit vector A has to be orthogonal to the integration domain R, so let's find out about this R first. So let's find out about this integration domain R. And as you know, this integration domain R is going to be the projection of the surface onto the xy plane. Alright, so this R right here, projection of S on xy plane. Okay, so we need to find that projection. So let's put a light source at the top of this ball. So let's have a sun right here. And now let's find the shadow of this ball onto the ground. Of course, it has to be this shadow right here. Okay, down here. Alright, so that is the projection of this surface onto xy plane. And looking at the size of this circle, we know this is a circle of radius 2. So we have this equation right here to explain about this circle that we have. A circle of radius 2. Alright, so we have this R on the xy plane. So we know that a hat has to be orthogonal to this r right here. So a hat should be something like this. Okay, so this is a hat, and of course it's going to be equal to k hat here, orthogonal to xy plane. Okay, so let's put all the information here. We know that a hat is going to be equal to k hat, just one component. And r is going to be the circle of radius 2. Circle of r equal to 2, centered at the origin. Centered at origin 0, 0. Alright, so we have all the information. Now let's put everything into the formula. Alright, now what about we find out about this gradient of f? So we need this gradient of f inside the formula. Let's find out about that. So first of all, let's find gradient of f. It's going to be equal to partial derivative of f with respect to x, I component, plus partial derivative of f with respect to y, j component. And last component, partial derivative of f with respect to z, k component. So let's find this gradient of f. So I'm supposed to diff this f right here with respect to x. So I get 2x out of that. So that is the first component. Gradient of f equal to 2x I. Now second component, partial diff of f with respect to y. Back to here, diff this with respect to y, I get 2y. So that is the second component, 2yj. And now I need to diff this again with respect to z, and I get minus 1 this time. So last component is going to be minus k hat. Alright, not too bad. What about I put the whole notation here? Gradient of f with x, y, and z. Alright, now the next term that we need is the gradient of f. Oh, by the way, we are supposed to find the absolute value of the gradient of f. So let's find that. Okay, absolute value of gradient of f is going to be equal to the square root of each component square summed together. So start with the first component, 2x square. 2x square plus the second component square, 2y square, plus the last component square, that is minus 1 square. So in the end, I have this gradient of f, absolute value equal to square root of 4x square plus 4y square plus 1. Okay, that is the first component in the formula. So now let's take a look at the second one. That is the absolute value of gradient of f dot with a hat. And in this case, it's k hat. So I'm supposed to dot gradient of f right here, this one, with k hat. Dot this with k hat. Of course, I get minus 1 out of that. So from this, I know that gradient of f dot with the k hat is going to be equal to minus 1. But in the end, the absolute value of this, absolute value, gradient of f dot k hat is going to be equal to just 1. Alright, we had this minus before, absolute value of that is just 1. So we got all these terms. Let's put everything into the formula. So let's construct the formula down here on the left hand side. So it's going to be, okay, area S equal to double integral of the absolute value of the gradient of f. So it's going to be this term right here, square root of these whole terms. So let's put that into the formula. Square root of 4x squared plus 4y squared plus 1. And divide this by the absolute value of the gradient of f dot with k hat, and that is equal to 1 right here. So we have this divided by 1, and we don't need that, so let's take that out. Okay, this is gone. We integrate this with respect to differential area over the integration domain R. And let's make a note that this R is circle of radius equal to 2. And we are supposed to solve this. Okay, this one right here. Now everything is ready. Alright, at this point I look at the projection and I see this R right here. This R is a circle. So to continue with this calculation, I think I'm going to go with the double integral in polar form, and that should make the calculation much easier to manage and execute. Let's write down here that we are going to take polar form instead. And the reason for that is because the shape of the integration domain R is a circle. Now for the polar form, everything has to be expressed in terms of radius R and the angle theta. We have covered the double integral in polar form long time ago, so if you forgot about that, you can always look that up. Now let's construct the double integral in polar form down here for the area S. So we have the same area S equal to double integral, and with this integral everything has to be expressed in terms of R and theta. Now looking at this, I need to transform everything I have over here into R and theta, and I am going to use the relationship between polar coordinates and the Cartesian coordinates, and that is R squared equal to x squared plus y squared. And with this, I know right away that these two terms right here add up to be 4r squared. This is equal to 4r squared, and that is the first term inside the square root down here. Okay, first term 4r squared, and of course I have this 1 right here, so let's add 1 into this square root, plus 1. Now for the differential area dA, this one has to be expressed in terms of R and theta too, and we have this relation right here, dA for the polar form equal to r dr d theta. So let's use that for the integration down here, r dr d theta. Now everything is expressed in terms of radius and angle. That is good. Now let's take a look here. We are going to perform the integration twice with respect to r first and then theta. So we need to specify the range of the sweeping for each variable. So let's start with the radius, the range of the radius. R starts equal to what value and ends at what value. And same for the angle theta. Theta starts at what value and ends at what value. To determine the range for each variable here, we need to look at the integration domain R, and let's take a look at how we sweep the whole region with each variable. So first of all, we are going to sweep the radius, and as you can see here, this is a full circle, whole area, which means that we have to sweep starting from the origin outside to the circle of radius 2, the circumference of that. So ends here. This is the sweeping of the radius starting at r equal to 0 at the origin, r equal to 0, and ends at the circle of radius 2, which means that r ends at 2 as well. Now for the angle, as you can see here, once again this is a full circle. So you have to sweep the angle starting from the x-axis all the way and comes back to x-axis again, and that's why we cover the whole circle. So theta has to start at 0 and ends at 2 pi, whole circle. Now everything is ready. Everything is expressed in terms of r and theta, and all the ranges for the boundaries, they are there. Now right now we just need to solve this integral. But looking at this, I think this is a little bit too complicated for me. Let's take a look here, all these terms inside the square root. It's going to be difficult to integrate this. So let's apply some technique to simplify this. Let's use substitution to simplify this one. So what about we assign u to be equal to 4r squared plus 1. Okay? 4r squared plus 1. And we are going to differentiate this u with respect to r. du by dr, we get 8r. And with this we know that dr is equal to du divided by 8r. And we can use this dr equal to du divided by 8r right here. Okay, let's put everything we have so far into this expression. Okay, let's split the screen right here. Okay, this is going to be equal to same double integral. And r starts at 0, ends at 2, sweeping of the radius. Theta starts at 0, ending at 2 pi, sweeping of the angle. Now we put u into this term inside the square root, so we have square root of u. Okay, we have square root of u here, and we still have r, and with this dr right here, we put this in, dr equal to du over 8r. So let's use that, dr equal to du divided by 8r. And we still have this d theta, so let's put it there, d theta. Maybe we got lucky, these two r's cancel each other, so let's do that. R right here and r right here. And I have this constant value of 1 over 8. I am going to bring that outside of the integral to keep the calculation simple. So let's bring this 1 over 8 outside, and we still have this double integral, okay, of this square root of u, du, d theta. Alright, r equal to 0, r equal to 2, theta equal to 0, and theta equal to 2 pi. Now we need to integrate this square root of u with respect to u, and that should be easy, right? So u, square root of u, this is u to the power of 1 over 2. We integrate this, we get u to the power of 3 over 2 equal to u to the power of 3 over 2 divided by 3 over 2, or it's the same as the multiplication by 2 over 3. Okay, and we need to evaluate this at two values of r equal to 0 and r equal to 2, and we still need to integrate this with respect to theta from theta equal to 0 and ends at theta equal to 2 pi. Okay, let's put this one right here, theta equal to 0 and theta equal to 2 pi, and we still have this 1 over 8 outside. Right, let's not forget about that, 1 over 8 outside. As you can see here, I still have this 2 over 3 constant inside. Let's bring that outside too, so we keep all the constant together. So this one is going to go outside, and it becomes 1 over 12, because this one cancel with this, becomes 4, and 4 with 3, it becomes 12. So let's change all of this. Let's get rid of all of these constants. Okay, outside it becomes 1 over 12. Okay, now let's continue with this. We are supposed to evaluate u to the power of 3 over 2 at two values of r. And as you can see here, we still have u right here. So we need to put r back into this expression. So we are going to put this back. U equal to 4r squared plus 1. Okay, this is going to be equal to 1 over 12 integration from theta equal to 0 to theta equal to 2 pi. And now u equal to 4r squared plus 1. So let's put that right here. 4r squared plus 1 to the power of 3 over 2. And we are supposed to evaluate this at two values of r equal to 0, r equal to 2. Still need to integrate this with respect to theta, d theta. Alright, now r equal to 2 goes in. This becomes 4 and becomes 16, so in the end we have this 17 for the first term. 17 to the power of 3 over 2. Now the second value of r goes in, r equal to 0. It goes in here, it becomes 0. So we have the second term, minus 1 to the power of 3 over 2. And we still need to integrate this with respect to theta. Okay, with respect to theta, from theta equal to 0 to theta equal to 2 pi. And we still have this constant outside, 1 over 12. Now, as you can see here, these terms inside, okay, let me fix this one a little bit too big, 17. So these two terms inside, they are constants. So why don't we take them out to keep the calculation simple? So this is going to go out to the outside of the integral. So it becomes this terms. 17 to the power of 3 over 2, this is equal to 17 square root of 17 minus 1 divided by 12. And what we have left here is the integral of d theta from theta equal to 0 to 2 pi. And since we have nothing inside this integral, this is just going to come out to be equal to 2 pi minus 0, or just 2 pi. And this is going to cancel with this 12 right here, and we have 6. So in the end, we have this as the answer. 17 square root of 17 minus 1 times pi. This whole term is divided by 6, and that is the answer for this example.